Okay, I see 3 o'clock, so I think you can go ahead. The next speaker is Qiaosheng Zhang or Eric from here at NUS where I work. And you tell us about covert identification over binary input channels.
Okay, thanks for the introduction. Hello everyone, my name is Qiaosheng Zhang. I'm from National University of Singapore. Today I'm very happy to share our recent work, Covert Identification or binary input discrete memoryless channel with you. This is joint work with Professor Vincent at National University of Singapore. So as you can see from the title, we are studying the so-called identification problems in this work. So this identification problem is different from the classical Shannon's transmission problems. So in Shannon's problems, we have a message, and the sender will send the message, use an encoder to encode the message to a lengthen sequence X, which is passed through a channel WY given X, and the channel output is denoted by a lengthen vector Y, and the receiver uses a decoder to decode the message based on Y. So the goal is to ensure that M hat equals to M. So equivalently, the goal is to ensure that the probability that M hat does not equal to M goes to 0 as n goes to infinities. So the identification problem is rather different. It was first introduced by Auschwitz and Dock in 1989. So in these problems, so the first part is the same. So we still have the message, and the encoder encodes the message to a lengthen code word X, and which pass through a channel WY given X, and the channel output is lengthen vector Y. So in these identification problems, we have many receivers where the number of receivers is exactly equals to the size of the message. And for each receivers, they are asked to answer one question. So for example, for the ith receiver, the question is whether the message M equals to I. So in this problem, we ask that for each receiver, they should be able to answer their own questions correctly. So their answer will be either yes or no. So formally, we define the error probability of the first count for the receiver I as mu I. So here mu I is the probability that the message M equals to I, but the receiver I answers no. And the error probability of the second count is denoted by lambda I. It is the probability that the message M equals to some other I prime, which is not equals to I, but the ith receiver answers yes. So this is basically the error probability of two counts for the ith receivers. So for the identification problems, our goal is to ensure that all the receivers, the two counts of error, mu I and lambda I, should go to 0 as n goes to infinity. And finally, it is worth noting that the goal of the transmission problem is harder than the goal of the identification problem, or vice versa. The identification problem is easier than the transmission problems. So this can be seen as follows. So if we have a scheme, we have a decoder which can output a message reconstruction M hat, which equals to M with high probability, then we can also use this decoder in this identification problem. For example, for each of the receiver, we will use the decoder that mentioned above. And for each receivers, they just use the decoder to first decode the message M hat. So once they know M hat, then they will know they should be able to answer their own questions. And as we have shown that this decoder ensures that M hat equals to M with high probability, then for each receivers, their message reconstruction M hat also equals to M with high probability, so they should also be able to answer their own question correctly with high probability. So this means that if we have a scheme for transmission, then we can also use this scheme to achieve the goal of the identification problem. But on the other direction, it is not true. So for example, if we have a scheme for the identification problems, but the scheme may not be applicable to the transmission problem. So this is because that even though we can ensure that for all receivers, the mu I and lambda I goes to 0 as then goes to infinities, but since the number of receivers is very large, so it cannot be ensured that all the receivers can answer these questions correctly. simultaneously with high probability. So it will be the case that some receiver thinks the message m equals to 1, and some other receiver may think that the message equals to I, which so these receivers cannot reach a consensus so that they cannot output a single m hat which equals to m with high probability. So that means they cannot this scheme cannot achieve the goal of the transmission problem. So basically, this is the difference between the transmission and the identifications. So since we have already seen that the identification problem is simpler than transmission, so a natural question is, what is the fundamental limits of the identification problem, and whether we can send a message of size even larger than e to the power n times the channel capacities over n channel uses. So in the first paper by Qiaosheng and Zhang, they show that indeed the size of the message can be much larger than this e to the power nc. In fact, its scale as double exponentially large. So the message m can be as large as e to the power n times some constant, which is denoted by CID, the identification capacity. So even surprisingly, this identification capacity is exactly equals to the channel capacities. So this result was shown by Qiaosheng and Zhang and Han and Verdu. So this is basically the classical transmission problem and identification problem. So in this work, we are interested in the covert identification problems, which is the main focus of this talk. So this problem is motivated by the recent advancement in the field of covert communications, which has recently attracted a lot of attention in recent years. So in the covert settings, the sender Alice may or may not send a message to the receivers. So we usually use a symbol lambda to denote the transmission status of the sender Alice. So when lambda equals to 0, it means Alice is silent. So in this case, the transmitted signal x is by default it's a less than 0 vector. And when lambda equals to 1, it means that the sender Alice is active. So in this case, Alice will choose the message m and use her encoder to encode the message m to a less than sequence x. And this sequence x is passed through a channel wy given x, and the channel output is again denoted by y. So there are many receivers where the number of receivers is exactly equals to the size of the message. And for each of the receivers, they have to answer their own question correctly with high probability. And on the other hand, in these communication systems, there may also exist some eavesdroppers who can eavesdrop the transmitted signal from a noisy channel WC given x, and the channel output is denoted by a length vector z. So we call this eavesdropper a warden. So this warden wants to use the knowledge of z to determine whether or not Alice is silent or active. But our goal for covert communication or covert identification, our goal is to ensure that the warden cannot reliably estimate this transmission status lambda. So in the standard covert literatures, so people often use KL divergence to measure the covertness. So we define the KL divergence between the distribution of z when lambda equals to 1 and the distribution of z when lambda equals to 0 as the covertness metric. And we hope that this quantity should be upper bounded by a covertness parameter delta. That being said, when Alice is silent, the output distribution of z maybe look like this, and when Alice is active, the output distribution of z may look like this. It is a little bit non-smooth because of the completed structure of the codebook that they use. So our goal is to ensure that this two distribution is as close as possible, and at least the distance between the two distributions should be upper bounded by the covertness parameter delta. So this is the basically this is a covert identification problems. So we want the receivers to be able to identify the message, and we also want the communication is covert with respect to the wardens. So this kind of problem can also find some applications in real-world scenarios. For example, the sender may be a commander and the receivers are some soldiers. So sometimes this commander would like to ask one of the soldiers to be prepared to strike. So in this case, the commander can use an identification code to and send a message m equals to I to the receivers. So once the receivers receive the signal y, so the ith receiver, the ith soldier, should be able to answer this question correctly. So this soldier should be able to know that the message m is equals to I, so that this soldier should be prepared to strike. So this is how we use the identification code in these scenarios. And simultaneously, since this is military instructions, so the commander does not want the wardens to detect whether or not he is sending some instructions. So we hope that this communication is also covert. So in this case, we would like to use a covert identification scheme to both convey the message and also to protect the communication from being detected by the wardens. So for these problems, we are also interested in how large can we choose the size of the message. So in our work, we give answers that the maximal size of the message scale as e to the power or the square root of n. So here, the square root of n is due to the covertness constraints. So we also identify this pre-constant here. So we define the so-called covert identification capacity, CCID, as the log of the maximal size of the message divided by square root of n. So our main result is as follows. So for any covertness parameter delta and binary input channels, wy given x and wz given x, the covert identification capacity, CID, is given by this formula. So it looks a little bit complicated, but roughly speaking, the first term is the weight constraint, which is due to the covertness constraint. And we can see that the first term is a function of the covertness parameter delta and also the channel wz given x, which is the channel between the sender and the warden. So the second term is this KL divergence between two distributions. So roughly speaking, it is the weight normalized mutual information between x and y. So as we can see that this is just a function of the channel wy given x. So this is just the channel from sender to receivers. So it's roughly speaking, it is a mutual information of x and y. So this expression is nothing but the maximized mutual information over all the input distribution px, which satisfies the covertness constraint. So this is our main result, and we also figured out that this covert identification capacity, CCID, is exactly equals to the covert transmission capacities for the covert communication problem, which was derived 5 years ago. So, but there is a key difference. So in the covert communication problem, they show that so when the channel wz given x is better than the channel wy given x, that is, the channel between the sender and the warden is better than the channel between the sender and the receivers, then in order to achieve these capacities, the sender and the receivers must share some shared key beforehand. But in our covert identification problems, so this capacity can be always achieved without the use of any shared key. So this is our main result. So next I will briefly introduce why it is possible to achieve a doubly exponentially large message set. So in most channel coding problem, we know that the encoder is always a deterministic encoder. That is, for each message, the encoder just maps the message to a lengthened code word. So we know that the total number of distinct code words which of length n is at most the cardinality of x to the power n. So this quantity is actually exponential in n, so that if we just use deterministic encoders, so the best we can hope for is to transmit, this quantity, these numbers of messages. But for the identification problems, we use so-called stochastic encoders, where each code word is actually a probability distributions. So for these problems, for each message, the encoder maps the message to a probability distributions over the product space Xn. So we call the code word U1, U2, and all the way to UM, and each of the code word is actually a probability distributions. So we know that if each code word is a distribution, then there are at most this number of distinct code words, which is x to the power n times x to the power n, which is double exponential in n. So if we use the stochastic encoder, then there's some hope that we can transmit double exponentially large message size in the identification problems. So this is a key part of the achievability of the identification problem. So next I will introduce our achievabilities. So from the covert communication literature, we have already known that in order to achieve covertness, the input sequence X to the channel should be of low weight. So specifically, the average Hamming weight of the input sequence should be upper bounded by L times square root of n, where L is a constant that we have already seen in the this covert identification capacity formula. So this L is just a constant due to the covertness constraint, and it is a function of delta and the channel WZ gamma x. And this claim means that even though the block length is n, but the number of non-zero element should scale as only order square root of n. So the sequence is actually very sparse. And in our work, we also use we do not use the IAD sequence, but we use a more structured constructions, so-called pause position modulation (PPM). So this is how a PPM sequence looks like. So we, roughly speaking, we just partition the block length n into L times square root of n blocks. And for each block, it contains exactly one non-zero element. So here we use this black box to denote the non-zero element. So as you can see, for each PPM sequence, the Hamming weight is exactly L times square root of n, because each block only contains one non-zero element. So we also define the PPM input distribution as the uniform distribution over all PPM sequences. And it has been shown by Bloch and Guha that using this PPM distribution this distribution can be used to achieve covertness in covert communication. So in this work, we also use these PPM distributions. So here is our achievability scheme. We use a random coding argument with PPM, and we set the size of the message M to satisfy these equations. So roughly speaking, we just back off the rate from the capacity a little bit by this 2 eta, where eta can be made arbitrarily small. And for each message M, we generate many we generate many sequence xmi, where I from 1 to capital N, and each of the sequence is generated according to the PPM distribution. So each of the sequence is a so-called PPM sequence. So here, this capital N is chosen to be e to the power 1 minus eta times the capacity. So we also back off from the capacity a little bit, and this capital N is chosen to be exponentially large. So for each code word, for each message M, the corresponding code word is denoted by UM, which is a uniform distribution over all the capital N sequences that we generate just now. So this distribution, this code word is just a distribution. And finally, we define the decoding region DI for the receiver I. So recall that recall that for receiver I, the corresponding message is m equals to I, and the code word UI is a uniform distribution over xij, where j from 1 to capital N. So we define this fxij as a collection of y sequence which satisfies this condition. And actually, roughly speaking, this set is the typical set of y with respect to the sequence xij, and this is typically usually called the information density decoder in the literature. So the decoding region for di is just the union of fxij for all xij that represent the message m equals to I. So this is our decoding rule. So for the soldier I, so if the receive vector y belongs to di, then the answer should be yes. And if y does not belongs to di, the answer should be no. So the error probability of the first cand, mu I, is actually the probability that the message m equals to I, but y does not belongs to di. And the error probability of the second cand, lambda I, is a probability that m equals to some other I prime, but the receive vector y belongs to the decoding region for I di. So this is a decoding rule for this problem, and we can show that with high probability, randomly generated code is a covert identification code, which means that for all the receivers, the error probability mu I and lambda I goes to 0 as n goes to infinity, and also it satisfies the coordinates constraints where the KL divergence between the two distribution of z is upper bounded by delta. So this is mainly because we use a low-weight ppm sequence so that we can ensure the coordinates constraint. And recall that we use the ppm sequence. It is actually a special case of the constant composition code. So using this special constant composition code is also critical in the proof of the achievability result. And we want to remark that if we use some IID codebook, then it may not be very easy to achieve this throughput. So this is basically the achievability part of this work. So next, I will introduce the Converse part of this works. So the Converse of identification problem usually relies on the concept of channel resolvabilities. So before introducing the channel resolvability, let me first introduce a relatively simpler concept called k-type distributions. So we are given a positive integer k. So if the distribution p satisfies that for all element x, the probability px is equals to 1 over k times some non-negative integer, then this probability distribution p is said to be a k-type distribution. So after introducing this k-type distribution, we're now introducing the channel resolvability lemma, which is also called soft covering lemma in the literature. So we are given a distribution px, which is on the product space xn, and now we consider two distributions on yn. The first distribution is py is induced by px as the channel. And for the second distribution, we describe as follows. We first sample k sequence x1, x2, all the way to xk according to the distribution px. And then we construct another distribution p tilde x as a uniform distribution over the k sequence that we generated just now. And then we notice that this p tilde x is a k-type distribution because it is just a uniform distribution over k element, and it satisfies the definition of k-type distribution. So the other distribution of interest is this p tilde y, which is induced by this p tilde x and the channel. So the channel resolvability lemma shows that if k is larger than some critical value, which is the e to the power the mutual information induced by px and the channel, then we have that the expected variational distance between the two distributions py and p tilde y goes to 0 as n goes to infinity. So now let me give a brief interpretation of these lemmas. So as we can see that this p tilde x is a uniform distribution over k sequence, and each sequence is generated according to px. So if we keep increasing the number of sequence, so this p tilde x will be getting closer and closer to px, right? And similarly, this p tilde y is also getting closer and closer to py, because p tilde y is induced by p tilde x and py is induced by px. So intuitively, if we increase k, then the variational distance between py and p tilde y is smaller and smaller. So this result shows that, okay, if k is greater than this critical value, then this variational distance on expectation goes to 0 as n goes to infinities. So this is very critical for the proof of our Converse result. So now let's consider any covert code, so which contains m messages, and recall that for each message, the code word is just a distribution over xn. So we can show that for any covert code, there must exist m prime such that at least m prime number of messages satisfy this property. So which property? So the corresponding code word, the mutual information induced by the corresponding code word and the channel is less than some threshold. And this m prime is also not too small. It is asymptotically equals to the size of m. And maybe for the remaining messages, for the remaining code word, the mutual information induced by this code word is greater than this threshold, but we don't need to care about this remaining code word, so that we can just remove this remaining code word. This is some standard expurgation argument in the literature. So now we end up with a new code which contains m prime number of code word and m prime number of messages, and such that all of these code words satisfy the property that the mutual information induced by the code word and the channel is less than the threshold. So now we would like to use the channel resolvability lemma to each of the code word u1, u2, all the way to un primes. So how do we use it? So here we just replace this px by u1, and now we consider two distributions. One is the distribution induced by u1 and the channel, and the second is similar to before. We first sample k sequences according to u1, and we construct a u tilde 1 as a uniform distribution of the k sequences, and the second distribution of interest is induced by this u1 tilde and the channel. So now we want to apply the last statement. So we notice that for u1, the mutual information is less than the threshold. So we just set this k to be slightly larger than this mutual information, than this threshold, so that the condition is satisfied. Then we have that the expected value of variational distance between the distribution induced by u1 tilde and the distribution induced by u1 goes to 0. And from this result, we also know that there must exist a 1 u tilde 1 such that the variational distance between the distribution induced by u1 tilde and the distribution induced by the code word u1 goes to 0. And also we know that this u1 tilde is a k-type distribution, so because here this u1 tilde is a k-type distribution. And similarly, for all the other code word, we can show a similar result because the mutual information is less than the threshold, and here the k is greater than the threshold. So this condition is satisfied. So we apply this channel resolvability lemma to all the code word u1, u2, all the way to un prime. So for example, for the last code word, there also exists a k-type distribution u tilde m prime, such that the distribution induced by the u tilde m prime and the distribution induced by the code word un prime, their variational distance is close to 0. So now we obtain some properties of the covert code. Then we also consider this covert code should also be an identification code, which means that it should satisfy the identification properties. So if the code satisfies these properties, then all the code word U1, U2, all the way to UN prime should be well separated. Here is illustrations. So this code word, each code word is a distribution, should be well separated. So their distance must be not too small. And furthermore, we know that this for example, for this code word U1, it's induced distribution, and there is also a k-type distribution U tilde 1 such that the induced output distribution is close to the distribution induced by U1. So it means that this U tilde 1 should be also close to U1. So in the figure, we just see that this U tilde 1 should be in distance close to this U1. And similarly, for all the other code words, there should be some other U tilde 2 and U tilde 3, and also with U tilde m prime, such that they are close to the original code word. And since this U1, U2, U3, Un prime, this code word should be well separated, and each of the blue distribution is also close to this red distribution. Then we know that these blue distributions, U tilde 1, U tilde 2, all the way to U tilde m prime, should be distinct. They cannot be the same. And also we notice that all of these blue distribution are k-type distribution. But we know that the number of distinct k-type distributions is at most the cardinality of x to the power nk. So we can use this observation to show that the number of code word or the number of messages in this code, so which is the size of m prime, should be less than or equals to x to the power nk, and then we can replace this k here to get this formula. So finally, we can just take double log of these quantities and normalized by square root of n, and then we take n to the infinity and also take some slackness parameter delta to 0, and we can see that the log of the message size divided by square root of n is less than the covert identification capacity. Also, finally, I just want to say that because the size of m prime is essentially the same as the size of m, so we can just translate this m prime to this m here. So this establishes the converse result. So this is the converse part, and this also ends the talk. So thank you.
Okay, thanks, Eric. So we're a couple of minutes over, but I think we don't have to worry too much about that if there's any quick questions. Okay, type in the chat or unmute. Otherwise, maybe I'll ask one quick one. So yeah, it's nice to see this like double exponential with the same constant, like you said the identification capacity equals the transmission capacity, and that's also the same in regular non-covert setting. Is that something we always see when we compare identification versus transmission? Like, is there any counterexample where that's not the case?
Oh, not the case. Okay,
could it possibly always be the case, and we can prove like a meta theorem that it is always the case?
Yeah, for discrete channels, actually, I don't know any counterexamples. But I think some group are studying the so-called deterministic identification problem. So where they do not allow the stochastic encoder, they only allow the deterministic encoder. So in their case, the capacity formula is slightly different.
And then is it only singly exponential instead of double?
Yeah, single exponential, but the capacity is larger than the Shannon capacity.
Okay, that's interesting. Okay, thanks. In the interest of time, I think we'd better move to the next talk. So thanks again.
Thank you.
With the next